Bismillahirrahmanirrahim. In this video, we'll learn about the binary search tree data structure. So, the binary search tree, we already know that this is a very useful data structure if we want to apply it for the searching and some dictionary operations. It can be used for the dictionaries, and it can be used for the priority queues and search minimum, maximum, and in order to find the predecessor, successor, and we want to insert some elements and delete some elements in an efficient way in a binary search tree. So what actually binary search tree is, what is the definition of the binary search tree? It's obviously is a tree. We know the tree data structure is very simple. It contains one node, right? In a binary search tree, the property of the binary search tree is it can have at most two children. That means it can have either zero child, one or two children, right? So at most a binary search tree can have two children, but in what fashion? If X is the root node and Y is its child, and then if Y is its left children, so then the key value of Y should be less than the key value of X if it is the left child, right? If it is the right child of its parent X, then the key value of Y should be greater than the key value of X. So this is a basic property of binary search tree. So in a binary search tree, so for example, if X is 10, then the left of X should be less than 10. So for example, is this 7, and right of 10 should be greater, for example, the 12. So this is the property of the binary search tree that we need to maintain. And in a binary search tree, all the operations are performed in order of h time, right? What is order of h? This is nothing but a log of n with base 2. How it is log of n base 2, if you are interested to know, we'll discuss it in few seconds. Just so you might wonder that why I have not put this less than, key of y is less than or equal to key of x if it is the left child, and key of y is greater than or equal to its key of x if it is the right child. You can do that, it is in the books, but usually we do not prefer to have the duplicate values in a binary search tree. But if there is a duplicate value of, then you can insert it into the right hand side of the right subtree. And then let's say, for example, if we have a binary search tree of form, for example, I am using this 15, and in the left side it is 6, right hand side I have one 18, then on the left I have 3, right, and in the right I have, for example, 7, in the right of 7 I have 13, and in the left of 13 I have 9, and in the left of 3 I have 2, right of 3 I have 4, and in the left of 18 I have 17, and in the right of 18 let's insert 20. So is it a binary search tree? That's the first question. Since it is fulfilling the property of the binary search tree, say for example starting from the root 15, left subtree is smaller than the 15. Yes, right subtree is smaller than the 15, and at every node you can check this property. If the property is violated, it's not a obviously binary search tree, but if the property is maintained, yes, this is a binary search tree. We can perform different traversals on this binary search tree. For example, we have one is the pre-order tree traversal, another one is the in-order tree traversal, and finally we have the post-order tree traversal, right? So what happens in the in-order tree traversal? In-order tree traversal, remember, this is nothing but in a form, in a way like node left right. What does it means? Whenever you are going to print a tree, or you are going to traverse a tree, or you are going to get the elements from a tree, what you need to go, first of all you need to print the node, then go to the left subtree, print the, do it there, and go to the right subtree and do it there. Like for example, in this tree, if we start from the root node, that is 15, right? So if we perform the pre-order tree traversal, what does it says? It says first of all print the node. So the node is 15, we did it. Go to the left subtree, and now we are here, right? We are in this way, right here. So what we need to do, again do the same thing, print the node, right? Print the node, that is what, 6. Then go to the left subtree of 6, that is this one. So print the node, that is 3. Go to the left subtree of this 3, that is, and print it, 2. Now go back, you have done the node, you have done the left, and go to the right now. So we did 2, we came back to 3, we already did it, and then go to the right side, that is 4, print it. Then go back to 3, we did it. Go to the 6, we already printed it. Go to the right subtree, that is what, 7, print it, 7. Go to the left side, so there is no left subtree of 7, obviously we are not going to print anything. Then go to the right subtree, that is 13, print it. And then go to the left of 13, that is 9, do print it. Go back, we already printed 13, 7, 6, 15. Go to the right subtree of 15, so right of 15 is 18, right? Then go to the left of 18, that is 17, and go back right of the 18, that is 20. So this is the uh, pre-order tree traversal. So if we talk about the in-order tree traversal, so how it actually works, it says left node and right. So what does it mean? First of all, you need to go to the left subtree, then print the node, then go to the right hand side. So let's say, for example, if we give it a try, say for example, in the if we start from the root 15, so the left go to the left of 15, that is 6. Go to the left of 6, 3. Go to the left of 3, that is 2. So first of all, you need to print 2 will be printed, then left node, then node of 2, the parent of 2, that is 3, 3 will be printed. Then right hand side, that is 4, 4 will be printed, right? And then go back to the, you have done the left of 6, now print 6. Then you have done it, and now what you need to do, go to the right. If you went to the right, right is 7. Now you have to go to the left of 7, but left of 7 is not present, so you need to print 7 here, because after left you have to print node. As you printed 7 node, go to the right, right is 13, but when you reach to 13, you have to follow the LNR again, so go to the left. So 9 will be printed, then node will be printed 13, then right of 13, that is not present, so go back to the 7, we already did it. 6, we already done it. So the node of 6, so parent of 6, that is 15 will be printed. Similarly, you go to the right, if you went to right, that is 18, left of 18, that is 17, then the node 18, then the right, that is 20. So you got the idea how we are going to do that. So quickly, very quickly, the post order tree traversal is left, then right, then node. At the end you have to print the node. So let's do it. So start with the 15, go to the left, 6, 3, 2 will be printed. Then you need to print the right hand side rather than the parent of 3, 2. So 2, 4, 3, go to the right of 6 before printing 6, that is 6. Go to the left of 6, that is not present. Left of 7, that is not present. Go to the right of 7, that is 13. Go to the left of 7, that is 9 will be printed. Then right of 13 is not present, so 13 will be printed. Then 7 will be printed, right? Then 6 will be printed, and then go to the right of 15. So when you go to the right of 15, that is 18. Go to the left, that is 17 will be printed. Then 20 will be printed, and then 18 will be printed, and at the end root will be printed, 15. So this is how we actually traverse the tree in different ways. Now our task is to basically write the algorithms and analyze the algorithm for these traversals. So first of all, if we talk about the order pre-traversal. So how we can write the algorithm? So if we apply the pre-order traversal on some node, it takes the root node as the um, argument, right? So you pass the just 1 minute. Okay, so you just pass the x as parameter, and let me just clear this as well and write it again. This is TT3 traversal, the short form, right? So what you are going to do in the pre-order, first of all, what you are going to check, if whatever the node that you are getting x, the root node, is it has some existence. If it is not equal to nil, if it is nil, then just do nothing. But if it is not nil, right, not nil means it has some existence, then what you need to do, you have to, first of all, what we were doing, we are going to print this x, right? And then after printing, what we were doing, we are going to call the same procedure on the left of x, right? So what I'm going to do is I'm going to call recursively pre-order traversal on left of x, right? And then the same will happen for the right hand side, pre-order traversal on the right of x, right? So that's how actually it works, and this is the simple algorithm for that. So what will happen if we are talking about the in-order traversals, right? So if it is in order traversal of x, right, then what happens? So same thing, so you will check if x is not equal to nil, obviously. Then what you need to do, then you need to call the in-order traversal recursively on the left hand side, then print it, then call it recursively on the right hand side. Simple. And if it is post order, then the print will be at the end. You will call the post order traversal on the left hand side first, then on the right hand side, then obviously you will print it. So that's very simple. Now what you need to do is prove the correctness of this algorithm. How you will prove it? Do some dry runs. Take some data, so for example from the previous slide, and perform the correctness check using the dry run. Okay. Now I am interested to know the time complexity of this algorithm. Since this is a recursive algorithm, you can find the recursive relation, isn't it? So if we find the recursive relation, so you can see if t of n time is required in order to complete this pre-ordered traversal on x, then how much time do you require for this print? Obviously this is simply every time you are going to check it, so you need to perform this for every node. So this require order of n times the number of nodes. So you are going to print every node, so this also require order of n time for every node. And here you are going to call it for the left hand side. So obviously the problem is divided by 2 here, so this is basically n by 2 time, right? Order of n by 2, and this also order of n by 2. And if you compute the recursive relations, that's now very simple, that is 2t of n by 2 plus order of n. And if you apply the master theorem to solve this recursive relation, you will get to know that is nothing but order of n, big of n, right? So you can easily print all the this is not h, this is n, right? N. So you can print it with this time complexity. Okay, so let's move next. If I am interested to find the minimum value and the maximum value from the binary search tree, I think that's very easy, very quick. So if you are going to find the minimum value, that is nothing but the leftmost child of in the left subtree of the node, that is the minimum value, and the rightmost child is the maximum value. So how we can find write the algorithm to find the minimum and the maximum. So for example, if I am interested to find the tree minimum on with some root node x, so if I am interested to find the minimum value in the tree, so what should I do? While left of x, okay, just a minute, while left of x is not equal to nil, until the left is not nil, you are going to the left and it is not nil, then what you need to do? Okay, so what you need to do is assign left of x to the x. You know why? Because next time you are going to get the next iteration. And finally, when it approaches to nil, so for example, if this is the tree and this is the tree, for example, this one. So if this is the last node, then it will not have any children except the nils, right? We already know that. So it contains the nil, right? Nil children. So once it gets nil, what it need to do? Just need to return or the print. Return x. That's it. So isn't it difficult? No. So what's the time complexity? Sure. So you can simply see that we are doing the half job. Actually, that is nothing but order of h, the height of the tree, right? So whatever is the height of the tree, it will go up to that point, right? Okay. So what if I want to find the tree maximum? So what you will do? Obviously, simply you will replace the left with the right, and if right of the let me just write it over here. So if for tree max value on root x, so if while right of x is not equal to nil, so keep doing this, right? And what is that? So assign the x to the assign x with the right of x, right? And finally just return it once you get it, right? Return x. That's it. So this is very easy, right? Okay, let's move next. So if you want to find some element in a tree, or simply I want to perform a search on a tree data structure, so how you can search from a tree? So for example, if you have a tree something like this, and then you have some elements here, some here, and so for example something like this, and this is so for example 90, and this is 80, this is for example 90, okay, this is 100, right? And this is for example 70, this is 85, and this is 82, right? Okay, and if this is 100, say for example this is 95, sorry, 95, so this is for example 120, this is for example 97, right? So if this is a tree and I am interested to find 85, we already know how to do that since our data structure class. So we'll start searching from 90, we'll compare it with 85. 85 is smaller than this, we'll go to the left subtree and we'll keep doing this until we find the element, or we found the nil. That means we cannot find the element in this tree. So this is the logic behind that. So how to write the algorithm for this? There are two approaches to write the algorithm. One is the iterative approach, and another one is the recursive approach. So let me discuss with the recursive approach. You have to write it with the iterative method, right? So if I am interested to do tree search, I'm sorry, I cannot write very well on the screen. Tree search with I want to find from the, I will start from the root. Obviously I will give it the root from where I have to start, and I will give the key element as well. So that I want to search k from a tree with the root x. So what I need to do is, if if x is equal to nil, if either x is nil or you got the k at e of x, right? If this is true, then what you need to do? Simple, you got it, return x. But if it is not true, you are not getting the key at that point, or it is not nil. So what do you need to do? So now you have to compare if the key that you are interested to find, to search, is if it is less than the key of x, then what you need to do? You know very well. You have to move to the left subtree, right? Then return with what? Tree, recursive call of tree search with left of x with key value, right? So you will return it. So if it is not true, if k is not less than key of x, then else obviously you will return tree search with right of x with key value, right? So simply that's it. So what's the time complexity? Obviously we are, if you can compute the recursive relation, that's very, if t of n time is required to search a key from this, then this is simple order of 1, right? So that is nothing but 2t of n by 2 plus 1. So that is nothing but order of log n, or in short order of h, if you solve it using master theorem. So how is order of h is equivalent to log n? We'll figure it out soon. Okay, then now you have to write the equivalent iterative algorithm for research. It is given in the book, by the way. If you open the book, and you will find it. Okay, then one important concept, that is the successor of a node. Successor of a node x. So how actually it works? Okay, before going to the successor, let me just draw one tree, the tree that we already have in the previous slides, and then we'll solve it. Say for example, okay, so the tree, for example, I have 15, the left of 15, right of 15, left of 15 I have 6, the 3 and 7. Just give me a minute. Okay, this is 3. Okay, then 2 and 4, and the left, there is no left subtree of 17, and there are 7, and right subtree is 13, and the left of 13 is 9. Oh, come on. Okay, so let me also here is 3 and write it again, 13, and right is 15 is 18, and left of 18 is 17, and right of 18 is 20. Okay, so in this tree I am interested to find the successor. What is a successor? Remember, there are 3 rules to find successor. Remember these rules. I cannot write it in detail here. So number one, if you are interested to find the successor of a node whose right subtree is present, right? Whose right subtree is present, then the minimum value from the right subtree is the successor of that element. For example, I am interested to find the successor of 6, right? So the successor of 6 has a right subtree, right? If it has a right subtree, then what? whatever is the minimum element of the right subtree, that is 7. 7 is the successor of this 6. That's a very simple rule. So the rule is very clear. If some node X has a right subtree, then the minimum element from the right subtree is the successor of that node. Okay, but the problem is, for example, let's take one more example. 15. So what's the successor of 15? So right subtree of 15 exists. So the minimum element from the right subtree, that is 17. 17 is the successor of 15. Clear? Now, what happens if the right subtree of that node is not present? Then there are two cases. So for example, I'm interested to know about okay, 13, right? So 13, okay, but before 13, let's start with 2. Okay, 2. So if the node 2, I am interested to find the successor of node 2. So is the right subtree of node 2 exist? No. If the right subtree of the node is not present, and now we have to check. Now there are two cases. If the right subtree of the node is not present and that node is the left child of its parent. I repeat, if the right subtree of that node is not present and that node is left subtree of its parent, then its parent is its successor, right? For example, in case of 2, what's the successor of 2? 2 doesn't have any right subtree and it is the left child of its parent, so its parent is the successor. For example, the 3 is successor of 2. For example, 9. So the right subtree of 9 is not present, right? So and 9 is the left child of its parent. So the parent of 9 is its successor. 13 is its successor. Similarly, 18 is the successor of 17. You can find it out. Okay, now in another case, for example, if there is a node whose right subtree does not exist, for example 13, right? Right subtree does not exist and it is the right child of its parent, then what happens? In case of 13, the right subtree is not present and 13 is the right child of 7. So what is the successor of 13? Then you have to walk 13, you have to find the ancestors of 13. So what are the ancestors of 13? 7, 6, 15, right? All are the ancestors. So the rule is, if X does not have the right subtree and X is the right child of its parent, then the lowest ancestor's parent is its successor. For example, what is the lowest ancestor of 13? So you can see 6 is the lowest ancestor of 13. So parent of 6 is the successor of 13. So 15 is the successor of 13. Similarly, let's see 4, right? So 4 does not have the right subtree, but 4 is the right child of its parent, right? So whatever the lowest ancestors. So the ancestor of 4 is 3, 6 and 15. So which one is the lowest? 3 is the lowest. So parent of 3 is the successor of 4. So 6 is the successor of 4. So these are the simple rules. Okay. Similarly 20, right? So 20, let me make it very clear. The largest element in a key does not have any successor. Straightforwardly. Let's see 20. So 20 does not have the right subtree. Agree? Okay. And 20 is the right child of 18. Agree. Now the lowest ancestor. See what are the ancestors of 20? Ancestors of 20 is 18 and 15. So the lowest one is 15. So parent of 15 is the ancestor of the successor of 20. So parent of 15 does not exist, that is nil. So that means the largest element in a key does not have any successor. These are the simple rules. Let me repeat. Number 1, if you are interested to find the successor of X and X has a right subtree, then the smallest element in the right subtree is the successor of X. But if the right subtree does not exist and X is the left child of its parent, then its parent is its successor. And if the right subtree does not exist and it is the right child of its parent, then the lowest insister's parent is its successor. Simple, right? So let's write the algorithm. The logic is clear. I think you can write the algorithm. So the logic is clear. So let's write the algorithm, how we can do that. So step number one. So first of all, let me check if X has a right child or not, right subtree or not. So how I can check if right of X is not equal to nil, right? Then what we need to do? It means it has a right subtree. Then it's very simple. We know return what? Minimum of X, of right of X, sorry, right of X. That's it, right? Now the second rule, if it does not have a right subtree, it means the condition is false. So for that, what we need to do is I'm going to write y, place the parent of X in y, right? So whatever the value you are for X value for this thread you are interested to find successor, put it in y, the parent of that X in y, and then do some work. What? While y is not equal to nil, and this is and not or, right? And X equal to right of X, right? If this is true, then assign the y value to X, right? And update y with parent of y, right? And finally, when this loop is over, return y. So this actually summarizes the last two rules. This is for the rule number one. If it has a right subtree, okay. If it does not have the right subtree, then you need to check. If it is a left child of its parent or right child of its parent, this pseudocode is for that. Your task. First of all, do the dry run and prove the correctness of this algorithm, right? You can take the same BST that I have drawn here in this slide. So you can choose the same, do the dry run and prove the correctness. Secondly, what's the time complexity? Yes, this is interesting. You have to find it out. Okay, so now, what you need to do is, I think this is your assignment. Whatever I am giving you the homework, I will grade it with the 5 marks, right? So you have to give the answers for this. Okay, so now one thing, another concept is one is the successor, another is the predecessor. Oh yes, so you need to find what is the predecessor, and you have to write the algorithm for the predecessors as well, right? So make the notes that what I am asking to do as a homework and to submit me, right? Number one, you have to dry run this successor algorithm, compute the complexity, and also find the algorithm for the predecessors, right? Okay, moving next. So how do we actually create this to insert an element into a binary search tree? We already know the logic. If it is the first element, it means it will be the root of the tree. If it is not the first element, then what? Then if we will compare the element with the root, if it is the smaller than that, we will place it to the left hand side. If it is greater than that, we will place it to the right hand side. And we will keep on repeating this until we get the nil component, and we will add it there. It seems easy, right? The logic is very, very clear. How to write the algorithm? That's one of the important things. Okay, so that algorithm I have already mentioned all these algorithms in the slides that I have already uploaded in the LMS. So do see the slide number 14. I have mentioned the analysis, the pseudocode of the BST insertion. So in that, this logic is very simple, very same that I am telling you. If it is the root node, you will insert it as the root. If it is not the root node, you will find the accurate place for that. And then it is also written in the slides that the complexity of insertion is order of h, right? So you need to cross verify it, you need to prove it that yes, it is order of h, right? Similarly, the pseudocode of deletion is also mentioned in the slides. So you need to understand the deletion procedure as well. Let me tell you the basic cases for deleting an element from the deleting a node from a binary search tree. Number one, if it is a leaf node, no worry about it, right? If it is a leaf node, just delete it, no problem at all, right? But then how you are going to find that is it a leaf node or not? Obviously, you will check whether it has a left child or a right child. If it doesn't have both children, it is a leaf node, you can simply delete it. But if that node X that you want to delete has only one children, right? No matters if it is X or Y, the left or right, right? If there is only one child, it's very simple. If that node you want to delete it, this node, and it has only one child, left or right doesn't matter. Then what you need to do is just connect the pointer of that node with its parent of X that you want to delete. So connect it here and then simply delete it. Simple. No, nothing to do, nothing to worry about it. But the problem is when this node X contains both children, right? Both children. Now you cannot simply connect both children to its parent, right? Then what you need to do? What you need to do is for that node that you want to delete, you need to find the successor of that node and swap it with its successor, and then then check what case is it in the previous two cases, and then perform the action accordingly, right? So if the node X contains both children, what you need to do is you need to swap that node with its successor and then check back again whether it becomes a leaf node or it contains a one child or it contains a two children. So you need to repeat it until you get either a leaf node or you get a one child, right? So this is how the delete procedure works. Okay, and that's all for now. If you have any questions, we can have the live session for question and answers, or you can just comment below this video. So I will answer those questions. So this is all for binary search tree and up till now. But then there is another problem. Okay, one thing I have still remaining, that is how this order of h is equivalent to log of n, right, base 2. Well, this n is nothing but number of nodes, right? So for example, I have a tree. Here, right? If height of the tree is this represent to the height of the tree, and this represent the number of nodes, right? Let's say if height of the tree is 0, what would be the maximum nodes? 1. You can see this is height 0 and the maximum node is 1. If height 1, what would be the maximum nodes? Right? You can see if height is 1, the maximum, this is height 0, this is height 1, right? So maximum nodes could be 3, maximum, right? So what if we have height 3, right? Height 2, sorry, height 2. What would be the maximum number of nodes? Maximum number of nodes are 7, isn't it? So similarly, you can extend it. If the height is 3, what could be the maximum number of nodes? It could be 15, right? If the height is 4, so the maximum number of nodes would be 31. So if you will place this in a mathematical relationship, so you will see h is nothing but the log of n base 2. You can compute it. So if you compute log of 31, that is nothing but 4, right? So that's why this order of h is equal to log of n, right? Now What is the problem of the binary? These are the benefits, right? What is the problem of the binary search tree? We use the binary search tree for the searching process, for the efficient searching in order of h time, that is log n, right? But what happens if the tree is the linear tree? For example, tree is something like this. This is 1, 2, 3, 4, 5, 6, and so on. And I am interested to find 6. How much time will it take? Nothing but order of n, isn't it? So if why this is the problem? Because the tree is not balanced, right? If the binary search tree is not balanced, we cannot apply, we cannot get the appropriate results. So then what we need to do? We need to balance this binary search tree. So the next topic is how we can balance the BST, right? So there are several ways. For example, we will learn about AVLs, right? We will learn about RB trees, right? Where there are other methods like split trees and others. So these two we will focus in our course, and the next lecture will cover these two topics. Thank you very much. Take care up till then.